What we're going to do right now is we are going to first graph the sine parent function. I'm going to graph a single cycle to the right of the origin, and then I'm going to graph another cycle to the left of the origin. That means since the cycle, or the length of the period of a sine wave, it's a wave, is from 0 to 2 pi, a full revolution of a circle. Remember, the unit circle does not live in the same universe as it being on a plane as like every other graphed function. We're using the plane, the x and y axes, to help us as a guide, but it's not a graph. It's more like the way a bar graph is a graph. It's not a function. A bar graph is data collected and organized on a graph. That's what the unit circle is. The x's, the y's, it's not the same as an x and a y from an equation placed on the x and y axes to make a graph of a function. That's a different visual, okay? The unit circle, it's a graphic organizer. It's a tool to help us remember. It's like a clock. Cyclic, we put it on a wheel to make our lives easier. So we're gonna do one cycle to the right, one cycle to the left. So really my x-axis, or my input or independent axis, my domain, I'm gonna look at temporarily only between negative 2 pi to positive 2 pi, or maybe this way for your view. And that doesn't mean the graph doesn't go on indefinitely in both directions. It does, but we can only draw so much, okay? Now, when I draw a parent function, remember the parent function is the version of the equation with no special transformations applied to it. Transformations include translations or shifts, which is horizontal shift or a vertical shift, move it left, right, or move it up or down. It does not include any reflections. Again, that could be a vertical reflection or it could be a horizontal reflection. And it does not include any stretches, vertical, compressions, vertical, or stretches, horizontal, or compressions, horizontal. It's just plain Jane, okay? So the parent function, in this case, we're gonna start with sine. I guess I could do, I'm not gonna put them both on one page. I'll just kind of draw pretty big so I can label it. Y equals sine. Now, I could call it theta. I am gonna switch it to an X right now, but X still does represent our input. And what do we put into a sine function? Angles. When you graph trig, you don't use degrees, okay? You're not gonna count up to 360 on this axis, okay? We do radians. Radians are a unit of measure that actually has no unit. So it makes sense for a graph. It's very important in that regard. If I look at this as being in, maybe you think of it as vertex form, you guys might think of H and K as being your vertex, where H was your left right shift and K was your up down shift or transformation. We could kind of think of it as like a vertex form, or we could call this transformation form, you know, because it doesn't really have a vertex the way a parabola will have a vertex, or an absolute value function as a vertex. It's like the absolute lowest point pulled all the way extreme in one direction. It's not the same when it comes to sine. So I can call this transformation form. I'm gonna put a little note of what letters I'm gonna use for that. So transformation form, I might call Y equals A sine parentheses B, another parenthesis, X minus H plus K. A affects our graph as a vertical stretch, compression, or reflection. B affects our graph as a horizontal stretch, compression, or reflection. H is our horizontal shift or translation, left, right. Vertical transformation, translation, or shift, left, right. So A and K They're on the outside of everything. They affect it vertically. B and H are on the inside. It's going to affect it horizontally. So keep that in mind. In this example up here, right now, A equals 1. B equals 1 right now. H equals 0 right now. And K equals 0 right now. That means that where I begin drawing my graph is going to be at 0, 0. That's where I kind of think of my crosshair, my center point, where I'm calibrating to. And then these being 1 mean that it's the parent function, okay? Now, the best thing to do, if you're going to graph, and like I said, I'm going to draw 2 cycles. Usually I will just draw 1 to the right of the origin, but I want to draw 2 right now. When you're drawing a year from now or 2 years from now, you're like, oh no, I have to remember what the sine wave looks like. Wait, which one is it again? And you're trying to remember. Your best bet, this line of thought, ready? You're going to say sine. Sine is the y values on the unit circle, right? You're going to think about that. Close your eyes. Remember the unit circle. Y values. Go slow and don't shout out anything crazy over here. But this is where you start when you draw an angle in standard position. What's the y value here? What's the y value right there? And we're going to go around 0. Good. And then here it's 1.
0.
And
-1.
And then back to 0, right? That would be 1 full cycle. The input, or the x-axis, I'm just going to mark up quadrantal angles, which are the north, south, east, west guys, you know? So I got 0 right over here. Now I like 4. I also like 8 tick marks. I also like, well, I don't want to say tick marks, but sections. Because really, if you have 5 tick marks, you have 4 sections. 1 between these two, these two, these two, and these two. So the 4 sections are represented by 5 tick marks. And what are those 4 sections? They're really representing the 4 quadrants, because the quadrantal angles are what I'm marking up on here. So I like putting like 4 sections on my paper, or even like 8, because when I put a tick mark out here, another one out here, and I get that spacing fairly accurate, from there I just cut everything in half. So cut that in half, looks about even. Cut that in half, about even. And then I'm going to cut each of those in half. This way my spacing isn't too wonky, okay? You know how it goes, right? Like it gets gross. So we're there. That was 0. This is pi over 2. This is pi. 3 pi over 2 and 2 pi. And then this way, it's just going to go the negative angle. So now I'm going that way. So clockwise, as opposed to standard form being positive angle counterclockwise. So I'm going to the clockwise direction, and that is represented on my plane for my graph. Negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Keep in mind again, usually if I ask you to graph a cycle or over a single period of a sine wave or anything, I'm usually referring to this particular wave being transformed. It's important to know, though, that it extends in each direction, because we spoke about the horizontal stretches and compressions, and how that could influence the number of solutions you might have in a window. So say between 0 and 2 pi, you may have more solutions if you have a compression, and we'll talk more about that. So now here, what we'll do is we're going to, I think I used red crayon whenever we did sine, maybe? I don't remember. So I'm going to go ahead now and plot these over here that you guys just said to me. So on my y-axis, this is not necessarily going to be to scale. Oh, guys, I'm so sorry. It's so bright. Did it just get that bright? It's been that bright. No one said anything. Or did it happen gradually? With the sun, maybe? Guys, you should have told me. Oh, okay. Oh, the sun's coming out. Yell at me if it gets really bright again, because I don't necessarily look up, okay? Does anybody remember the decimal approximation for pi over 2? You can figure it out. It's half of pi. Just shout it out.
1.57.
Good. So it's approximately 1.57. That's approximately 3.14. Oops. 1, 4. This is approximately 4.71 and approximately 6.28. Okay. So if that's about 1.57, if I kind of want this to scale, it doesn't need to be. I'm just humoring the situation. 1 is going to be a little smaller than that, about, 2/3 of it. So that could be +1 and that could be -1. Since, think about sine. Sine is the opposite over the hypotenuse. The hypotenuse is the biggest side of a triangle. The sine of an angle, since the biggest side is the bottom of the ratio of the fraction, the sine of an angle can never be bigger than 1. Keep that in mind. So when I'm drawing these axes, I think about that. And it's going to oscillate. Think about the word oscillate and an oscillating fan. An oscillating fan is like this, back and forth all day. So it's going to oscillate between, because it could be -1 and 1 for its whole life. All right. Like bouncing around back and forth. Okay. So think about that. And that's going to also come in good with your knowledge over here when we do the reciprocals, because what do you know about the reciprocals of all the numbers between -1 and 1? Who can tell me something good? Think about that. I'm going to plot the points that we said before, okay? What can you tell me about the reciprocals of all the numbers between -1 and 1? Got an idea? How did I know? Is that Chris?
Yeah. Are they all greater than 1?
Or equal to, but
Greater
yes.
than or equal to 1.
Yeah, because the reciprocal of 1 is 1. Good. Chris, we needed a statue of like the thinker, but with Chris's head on it. He likes those like thought-provoking questions. So yeah, so pick a number between -1 and 1, right? Well, there's 0. The reciprocal of 0 is what? Anyone? Don't say the wrong thing.
Undefined.
Good, undefined, yeah. But then we have to say 1/2. Well, what does that become? 2. 1/3 becomes 3. 1/4, 4. So actually, the smaller the fraction gets, the bigger the reciprocal gets, right? 2/3 will become 3/2, and so on. So when we're drawing, not sine and cosine, but when we're drawing secant and cosecant, this might not be enough room because my picture of those are not going to be oscillating between here and here. Instead, the graph of secant and cosecant is everywhere but here. So you really need to think about that when you're setting up your paper for the graph, okay? Now, is sine ever undefined? Is sine ever undefined? Is there an angle between 0 and 2 pi that if you try to take the sine, it doesn't work? Or is it always defined? Do you always just get an answer? Any ideas? Any guesses? I see like some nodding and head shaking, but yes, it is always defined. Good. I see Catherine wrote that. Thank you. So here, now you want to try to make this smooth. There is a difference, especially if you're going to take calc. There is a difference between a function being smooth and a function that's not smooth. And by not smooth, we might be describing what is called a cusp or a node. And a cusp or node might look something like, a cusp might look like kind of like a widow's peak or like a bird. And a node might look like an absolute value function, kind of like that. Ooh, the sun's coming in the window. Okay, so that is not smooth. It's continuous, but it's not smooth. And in calculus, you want to find things that are, a lot of times you want to deal with things that are smooth and continuous. And we say that they are things that are differentiable on their domain. And differentiable means that you can define or determine the slope of a curve anywhere, which is some good stuff, okay? So this over here, what we just drew is the parent function of sine. So a year from now, if you forget, what does the parent function of sine look like? You could just do this in your head. You focus on the quadrantal angles and you kind of just dive right in from there and plot those and then carry on. Pi over 6 would be like somewhere over here. This would be pi over 4, pi over 3. Pi over 6, sine of pi over 6 is a half, so it should be about a half. Mine, is it to scale? Probably not. Pi over 4 is root 2 over 2, and that's about 0.7 whatever. Pi over 3 is a little closer to pi over 2, and the sine of pi over 3 is root 3 over 2, which is about 0.87, a little closer to 1. At pi over 2, it's 1. And then you repeat in quadrant 2, positive values going down. Then we hit the negative values till -1 and so on. Okay? So this parent function should make sense to you guys to some extent, right? Can you kind of wrap your head around it? If it was matching, you know, that's sine, that's cosine, you could probably figure that out. So now we're going to do one with all different transformations. I know we spoke about it already, but you're going to be a bit careful. Now, the stretches are pretty easy, or compressions. So are the reflections. The horizontal stretches and compressions are where it gets a little dicey. So here's something I want you to write down for sine. When you find sine, it has a period of 2 pi. But the formula, because I could even say normally it has an amplitude of 1. What's amplitude? Amplitude is the absolute value of this distance here, okay? So distance is positive anyway, but it's going to be how far it is from the middle of your graph to a maximum point. And then how far is it from that middle line of your graph to the minimum point? So normally the amplitude is 1. Amplitude is normally 1. But as a formula for future amplitudes, okay, you might want to say that the formula is A equals the absolute value of A. So whatever that coefficient is, which it could be negative, and that would just mean there was a reflection involved. If you take the absolute value of it, that is the amplitude. So this A here is amplitude. Okay. So I'm just going to put a little happy cloud around this. This all goes together. Now that is your vertical stretch and compression. Does anybody remember what the word is to describe this dashed line? There was like a fancy word, and then there was like a less fancy word. Even if you say it wrong and you sound like a silly person saying it, it's okay.
Miss Thomas, can you repeat the question?
Do you remember the fancy word for that dashed line that slices through? No matter where you move your sine wave, it goes with it. Like it kind of carries as like the new middle of your graph. So your sine wave is like weaving up and down through that right there. So like you're a dolphin, okay? And that's the surface of the water, and you're like jumping out, putting on a show for the people on the boat, and boop, 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 like this. So what is the name? There was a fancy name for that blue dashed line that I just drew in blue, and there was like a less fancy name for it. Anybody remember?
The sinusoidal function?
Sinusoidal axis, yes.
Axis?
Good. So it's a sinusoidal axis. So it's kind of like, it's not an asymptote, and it's not, every dotted line is there for a different reason. So an asymptote, like a vertical one, that's there like caution tape, okay? It's like, do not go here. This is a cliff and you're gonna fall off the cliff. It's undefined, you cannot go here. A horizontal asymptote, and we're gonna talk about this when we go to limits, a horizontal asymptote, that's more like of a trend. That's what's happening as you go out further and further and further toward either infinity or negative infinity. And we saw those, for example, in 1 over x, We saw those in exponential functions, like an exponential decay. As it decays, it gets closer and closer to zero, but it'll never be zero. So if you've ever consumed caffeine in your life, caffeine has a half-life of about like 4 hours or something like that. So half of it is gone at 4 hours after you consume it. And then 4 hours after that, half is gone. 4 hours after, whatever. It might be different for everybody, but something like that. So it's never actually gone. There's going to be trace amounts always. So we draw a dashed line, not because it can't get there, but because it's like magnetically drawn, literally drawn towards that. Okay. So y = 0 is now Zareen said the nice fancy phrase. It's called the sinusoidal axis. This dotted line is not something we avoid. This dotted line is not something that we're like getting closer to. It's more a dotted line to represent that middle of our graph. So it does have another name that has to do with the word middle. No one know? No one wants to shout anything out? The midline. Easiest name you would ever think of. Okay, so y = 0. If you want to sound fancy, which I like to say this one for some reason, I've always said it this way. I never called it midline when I was younger. It's always been a sinusoidal axis, but midline if you feel like you say it funny. You don't want to mispronounce it, okay? Now, that's y = 0, but as a formula, right now it's 0, but what do you think the formula could be? For that, y equals, what would the formula be? Based on A, B, H, and K, if they were involved. What would the formula for this blue dashed line? If I changed up some numbers, which number on that equation, A, B, H, K, or maybe a combination of numbers, will dictate where the blue dotted line goes? What is that formula? Any ideas? I think it's...
Would it be K because that's like the vertical shift?
Yep, y = K. So as a formula, y = K is going to tell you where you draw that horizontal dashed line. All of this is really important because you don't want to be that person that like draws this X and Y axes and like you drew too much space of one area and you didn't need it. Planning ahead, seeing this information like amplitude and the where the sinusoidal axis will be, it's going to be helpful. And now the period, okay? So here, the period is 2 pi because one of these numbers affects the period. So remember, the period is how long it takes for the sine cycle to begin repeating itself. So which letter affects, so the period is how long is it from start to finish? Which letter, A, B, H, or K, will impact the period of the sine graph? Which letter, A, B, H, or K, will impact the period of a sine graph? Remember, we're going to pull it either this way, make it big and wide, make it bigger than 2 pi, or we're going to compress it and squeeze it this way and make it smaller than 2 pi. The period is how long is it from start to finish. Give it a shot. Even if you're wrong, it's okay. I'm happy you tried. I mean, A is a... Go ahead.
I would probably guess A.
Well, A is affecting the amplitude, right? A is a vertical stretch or compression. And we said in the beginning that these things affected the, you can't see my whole screen, but these things out here were vertical impact. And then these inside here were more horizontal. Horizontal is inside this little house, HH, right? Vertical, vertical's outside. I don't know what to tell you. All right, like Verizon. Up in the sky.
So would it be B?
It is the B, the horizontal stretch or compression. Now, remember I called this the crazy house and I said everything's backwards. If this were a 2 and this were a 2, different things happen. If this were a 2, it was a stretch of 2. It got stretched out twice as much. However, if this is a 2, it's a compression by a half. That's why our formula for period is going to be 2 pi over b. If you divide by it instead of multiply by it, see here I'm basically multiplying by it, but do you see that multiplication? No. Why not? Because it's normally 1. So a lot of the things you guys graphed in the past, you did do this stuff. If you graphed a parabola the way I teach it through the pattern of the odd numbers, because that's how far apart all the perfect squares are, and then if we had a vertical stretch, you would double those numbers. Well, you took your original pattern, which was 1, 3, 5, 7, and you double it. 2, 6, 10, 14. So you multiplied it by a. Here, it's always up 1, down 1, up 1, down 1, up 1, down 1. So you multiply by a, it's almost easier. You don't have to know a whole pattern like a parabola that keeps going up and changing. Here, it's like this happens. And then what? The same thing. And then what? The same thing. Forever, right? So the A is involved in the formula for the vertical, and the B, instead of multiplying by it, we divide by it. And even that we've been doing, but if you had a parabola with a horizontal stretch inside, it would be because there was a half. If you divided by a half, you were multiplying by 2, and instead of going out 1, out 1, out 1, you went out 2, out 2, out 2. So we did do it, but because ones were involved, you don't see it. Okay, you don't see it happening. Now that we have a 2 pi, it really, ish is getting real. Okay, you can really see it. So this is the formula. So I should label that. So now for this particular, the period is 2 pi. Yes. But for a formula, I'm gonna put that in a little cloud. The formula is period equals 2 pi over b. Hopefully that's going to show up. Yeah. Okay. So here the period is 2 pi for this example. The formula is this. The midline is y equals 0 for this example. The formula is this. The amplitude is normally 1 in this example. The formula is this. The starting point. Okay. Our starting point right there. I'm just going to label it a little ST, like street. My starting point is when x equals 0 as a tick mark. It doesn't mean up and down 0. I'm not giving the y coordinate, so keep that in mind. It's at x equals 0. Which of these things affects that dot and where it goes? A, B, H, or K? Which thing affects that? As an x value. If I move it up or down, my x value doesn't change. So who cares about k? It's still there, right? And if I stretch it, multiply it, well, that's a vertical effect, right? You could just shout it out, guys, because I can't see the whole thing right now when I have it set up so I don't cut off the screen. I think somebody raised their hand. I lost it. Maybe. I could have sworn I saw. And then there's the B, which we said affects how long this is, how much it stretches out. But when you stretch out, you don't even change that starting point because you're stretching off of 0. So there's only one thing left. Anybody going to shout it out?
H.
Yay, H. So it really is whatever that H is there. But if it's like -2, you know, then, well, it won't be -2. But if it was like minus pi over 6, then it would go to the right pi over 6. So the minus sign's already built in. So my starting point as a formula, my first tick mark, okay, will be at x equals h. Some people set this equal to 0 to figure out what it is, like if it's messy. That's the formula for the starting point, okay, ST over there. Now, another thing that we find after we find the period, remember the alphabet, okay? LMNOP, next letter is Q. After you find the period, we're going to find a quarter of it, because if you know how long this is, divide it by 4 or multiply it by 1/4 to figure out how big each of these are, and bam, you could list out all of these little nuggets along the way. So the next thing after the period we're going to find is the quarter period, which is 1/4 of the period. And then that just tells us, I'm just going to draw a bunch of little Q's here for quarter period. Okay. Just because that comes after the letter P to help us remember. Okay. That all being said, you have the tools that you need right now to figure out a completely transformed sine wave. So I'm going to highlight the formula components. We have this. This is a component of it. We have our little starting point. Okay. We have our amplitude. We have our sinusoidal axis or midline. Starting point, we said right there. Amplitude. Right there. I guess I could just add one more thing. I didn't put the period on here, so right there. It doesn't matter which point you pick first for the period. Like any starting and finishing point, the period will remain consistent the whole time. Periods are there. Little Q guys over here. Am I missing any of the formulas? And then there's this main beefy guy over here. Okay. I think I highlighted everything I needed, right? So ready? I'm going to give you guys an example and then you're going to try it right now. Got 8 minutes. So I'm going to end this recording. And then when I go over the answer, I will record it, but I really hope that you guys could do it on your own. Fingers crossed. And let's do, as a part of your classwork / homework, you're going to submit your drawing of your sine wave that we're going to do right now. So if you're watching this video later, if this is something you're kind of following, it makes sense based on graphing, thumbs up. If you're like, no, thanks, I need help, put a thumbs down. Okay.